In previous lessons, we graphed polynomials, kind of like the one that you see here, using the zeros, the multiplicity of those zeros, the end behavior, why did I say that so weird? And so let's practice that for a little bit. Let's just graph this polynomial in the box here. So some things we know about this polynomial is that it has some zeros. Those zeros occur at x equal to 2, x equal to -3, and x equal to 5, because that's where each of the factors using the zero product property would be equal to 0. The multiplicity of each of these zeros is 2 for 2, since it has a squared right here. The x equal -3 has a multiplicity of 1, and x equal to 5 has a multiplicity of 1 as well, which means that at even multiplicities, the graph is going to bounce, and at odd multiplicities, the graph is going to cross over from negative to positive. For this graph's end behavior, we know its leading coefficient is going to be positive because there's all positive x values there, and that the degree of this polynomial is 4. So an even positive polynomial is going to have the end behavior of up, up. The very last thing we can graph here, just for an extra accurate sketch, is we can find the y-intercept by plugging in 0 to the function, which would make 0 minus 2 is -2 squared, 0 plus 3 is 3, and 0 minus 5 is -5. If we multiply all of that together, we are going to get -60. And so that's a ton of information. So if we go ahead and graph on an x and y coordinate these pieces of information, that we have a 0 at -3, at 2, and at 5. We also have a y-intercept of -60, and we know its end behavior is up, up. So we go ahead and start playing connect the dots. So we start at the very left end behavior, and we make it to the first point. -3 has a multiplicity of 1, which means I can cross over the x-axis there and make it to my y value. I can go up to 2, and 2 has a multiplicity of 2, so that means we're going to bounce at 2, but then we're going to have to cross again at 5, and then make it to my other end behavior. And here's a nice sketch of that polynomial. Now last class we were solving these polynomials, and really all we were trying to do is find these values that are called zeros of the functions, or where the graph crosses the x-axis. Now that's when we were solving equations. Today we're going to be solving inequalities for both polynomials and rationals. Now inequalities are going to look something like this. It says find f of x greater than 0. And when we're talking about f of x greater than 0, we're talking about where the y values are above 0, where f of x is positive, aka where this graph is above the x-axis or over the x-axis, where it's positive. And if it's asking you to solve an inequality that looks something like this, it's saying f of x is less than 0, so y's that are less than 0. F of x is negative, or that those values are below the x-axis. So what I want to do is I want to highlight these graphs so that I know where the graph is above and below. It's going to help us while we're learning. All day today, I'm going to be highlighting the parts of my graph that are above the x-axis in green. Green for positive, and I'm going to highlight the parts that are below the x-axis in red. Red for below. Now the parts that are at 0, okay, the zeros of this function, I'm going to go ahead and leave those blue today, which they're already blue, but remember those are exactly where the graph is equal to 0. So we have above parts of the graph, we have below parts of the graph, and we have exactly equal to parts of the graph. What this is going to allow me to do is it's going to allow me to answer questions about how to solve these polynomials from this graph. Now, we're going to answer these in interval notation, which means we're looking for the x value when these different properties exist. So the first one is asking for this function where it's greater than 0. Please notice this is the same exact example from the sketch that we just made, so I'm looking at this graph up here at the top. That's what I'm looking at. It says find the x value so that that polynomial that we just drew is greater than 0. Well, the color I'm using for things that are greater than 0 is green. So if I look at the graph for all the places on the x-axis where the graph is green, that means we're going to be going from negative infinity all the way up to the x value of negative 3. So from negative infinity all the way to negative 3. But negative 3 is a blue value, so I'm going to use a parentheses. And then we only have green again over here on the right side, which is from 5 to infinity, not including negative 3 or 5. Because those are blue dots, or those are where it's exactly equal to, and we only want where the graph is above 0. The next thing we're asking for is where the graph is greater than or equal to. So notice now I have two colors that I'm annotating this with, because it's greater than, that's where it's green, and it's equal to, which is where it's blue. I need to include all of those colors in my interval, which means my graph is going to go from negative infinity to negative 3 inclusive. I'm going to pick up my pencil, and the next time I have either blue or green is at the value of 2. But it's just the number 2 because I'm going to use a set that contains only 2. And then the next time I have either blue or green is from 5 to infinity. So notice how that or equal to part changes a lot about my interval. Because not only am I wanting the places where the graph is above or the graph is green, I also want the places where it's equal to 0 or blue, which includes this value of 2 because it's blue. That's where it's equal to. So greater than or equal to is all of those places right there. The next question asks for where the graph is less than 0, which is my red color. So the graph here is less than 0 from negative 3 all the way to 2, but then I have to pick up my pencil because 2 is not red, and then go from 2 to 5. Those are all of the intervals, all of the x values where the graph is red, or the graph is less than 0, below the x-axis. And if we look at the next question, it changes to less than or equal to, which means now I'm including both the red and the blue sections. So it's equal to negative 3. And then it's red or blue all the way up to the number 5, including 5. Now here's a moment that's kind of cool. Why did I not have to stop and talk about or include the number 2 like I did here in this domain? And hopefully you're like, well, Ms. Quigley, this graph goes from negative 3 to 5. We're coloring in on this number line all of the values from negative 3 to 5, including 2. Isn't that included in the interval from negative 3 to 5? So 2 is actually in here. We just don't need to talk about it because it is contained in that interval. And then last but not least, it asks me to find the values of x so that that function is equal to 0. In the places that it's equal to 0, which is what we had been finding in our polynomial unit, is where the graph crosses the x-axis, which is the set of numbers negative 3, 2, and 5. It's just the blue sections. Polynomial inequalities can be kind of complicated, but if you color code it for yourself and really know what the graph is asking for, above, below, or equal, you're really just matching up the colors or matching up the values of y there, which is pretty nice. So we're going to check out a couple examples. We're not filling out all of the examples on your notes that you have, so just bear with me here. In these two examples, this is example 3 and 4 on the back, we have a rational function here that I've already annotated for you, where it's above, equal to, and below the x-axis. And we have a polynomial here, and I've already annotated again, where it's above, equal to, and below the x-axis. Take a second and make sure that all of these answers make sense to you. F of x is, in example 3, is greater than 0, so the green parts are from negative infinity, which is over here, from negative infinity, all the way to the x value of negative 1. And then we turn green again after the x value of 0 until we get to the x value of 1. Those are all the places where the graph is green. For the second part, it asks me for where the graph is greater than or equal to, so I'm including both the green and the blue moments of this graph, which again is from negative infinity to the value of 1. We pick it back up at 0, but that one's blue, so I'm going to change that to a bracket because we're including the blue colors here. And then again to 1. This rational function is less than 0, this is part C, everywhere it's red, which is from -1 to 0, and then again from 1 to infinity, because it's going off screen here. The x value is going to go off to infinity. The next part is asking for where the graph is less than or equal to 0, which again is red and blue. This graph is red from -1 to 0, but including 0 because that's where it's equal to, and then again from 1 to infinity. Then last but not least, the only places where this graph crosses the x-axis or where it's equal to 0 is at the point 0, 0, so we include the x value of 0 in the set. Same thing happens for this last example 4, so go ahead and just pause the video and make sure these answers make sense to you. We can also solve polynomial inequalities algebraically. We'll get back to rational functions in a little bit, but let's just take a small little detour into inequalities algebraically. We introduced this in the P chapter, but like everybody felt like your eyes glazed over when I talked about it. So let's try this again. When we solve polynomial inequalities algebraically, we're going to be using a sign chart. A couple things we need to remember for a sign chart is just a couple of fun facts here. If you multiply a positive times a positive, you're going to get a positive. If you multiply a positive times a negative, or vice versa, you're going to get a negative. If you multiply a negative times a negative, you're going to get a positive. And if you have either a negative squared or a positive squared, that's going to be also positive. So we're going to be making sign charts for the different subintervals on our x number line that represents the different parts of a polynomial. To do that, we need to know the zeros of this polynomial. Now, so for a second, I want us to pretend like this is just a regular equation. Let's just pretend that this says x cubed plus 3x squared equal to 0. If we were just trying to find the zeros, we would factor and then use the zero product property to solve, knowing that the first part could be equal to 0 or the second factor could be equal to 0. These two numbers here are the zeros of this function. But we need to go back before we draw our number line and remember what this question is asking us for. This question is asking us for the polynomial that's greater than 0. Does it say equal to? No, it just says greater. So when I put the numbers -3 and 0 on this x-axis number line, I'm not going to include them. I mean, they're the zeros of it, but for what I'm looking for, we're not going to include these two values of -3 and 0 because we're only looking for where the graph is bigger than 0, not equal to. So for good measure right now, I'm going to let them be holes. They are not holes in the graph. They're holes in the kind of polynomial inequality we're looking for. What we need to do now is decide which of the 3 subintervals that you see here on this number line are above the x-axis, or which are positive. So we're going to take each subinterval and we're going to plug in a value to the function and just calculate the signs. We're not actually multiplying these out. We just need to calculate the signs if it's going to be positive or negative. In that first subinterval, a number I could plug in is -10 because -10 is less than -3 on a number line. If I were to plug in -10 to this equation, the factored equation where we have the parentheses, we'd have a negative number squared, and then -10 plus 3, that's still going to be a negative number. Negative times negative is positive, and then positive times negative, it's going to be a negative, which means this is going to be below the x-axis because it's negative. In the second subinterval between -3 and 0, I could plug in -1. Which means I'm going to plug in a negative number and square it. And -1 plus 3, that's a positive number. Negative squared is positive. Positive times positive is positive, so this is going to be above. Ding, 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 that's going to be a subinterval we want. And then the last subinterval, 3, you could plug in a 1, you could plug in a 10, you could plug in a 5. I'm going to plug in 10, which means we're going to have a positive number squared, and 10 plus 3 is still a positive number, which will give me a positive output. That's also above. And if we were to color in this number line, kind of the way we've been talking about domain all year, we're looking for where this graph is above, not below, but above. So our interval here, where the graph is above and above only, is going to be from -3 to 0, and then from 0 to infinity. Because I can't include those blue zeros, it's not asking me in the original problem if it's equal to, it's just asking me if it's greater than. So the trickiest part here is picking the numbers to plug into your subinterval. And really, you can plug in any number so long as it is on the number line in the subinterval you're trying to use. I recommend always using -10, -1, 0, 1, and 10 if possible, just because usually those are pretty easy numbers to plug into something. But like you could have used -2. You could have used 18,000. As long as it is in that subinterval, you can plug it in and test the sign chart. So again, I'm not going to kind of walk through all of these. I just want you to really look. I'm going to talk more about B than C, but C is there for you to look at. Number B, we're looking for where the graph is greater than or equal to 0. So I'm including the blue and the green parts of my graph. But we're going to do this algebraically. So here are the 3 zeros for this function: 2, 3, and 8. So 2, 3, 8. I put them on my number line. I needed to plug in a number in the first subinterval, in the second subinterval, in the third subinterval, and in the fourth subinterval. And that's what I did here. Here's the first, second, third, and fourth subintervals, and I plugged in those numbers. Once I plugged them in for the signs, I got for the first subinterval that it's over, second under, then under again, and then over. So here's what my number line looks like once I've filled it all out. And again, I'm looking to include in my final answer here in interval notation the places that are green and blue because it's greater than or equal to. So places it was above or equal to are from -infinity to 2, also the number 3, and then from 8 to infinity, which we've written here in our interval. Same thing for part C. So if you wanted to pause this video and kind of look at that one, you can. Obviously, I know you're probably scrambling to write it down. Just go ahead and do so. But let's end today talking about rational inequalities and how to solve them algebraically. Couple things to remember. Rational equations equal 0 when the numerator is 0. We can't divide by 0. So when this is equal to 0, which is what we want, we're really just trying to figure out when the numerator is equal to 0. That's what we want. And that being said, this is still important because it is a part of the domain of the function. We can't forget about that domain that the denominator cannot be equal to 0 because we're going to need that in our number line. Okay, so let's look at this first one. First things first, let's talk about the domain of this function. The domain of this function is that the denominator, again, cannot be equal to 0 because you can't divide by 0, which means x cannot be 5. And if I'm trying to figure out, just like we kind of did earlier, pretending that this is just a regular equation, I know that this this rational function is equal to 0 when x plus 9 is equal to 0, which means x equal to -9 is a 0 of the function. Cool, so here's my number line of things I know so far. I know that I have a 0 at -9. Sorry, I'll make that blue like normal. I have a 0 there at -9, and I have a hole in my graph at 5 because the domain can't be 5, period. Just can't be it. which means I have 3 subintervals that I need to test in a sign chart. The same way we did for polynomials, we're going to do for these rational functions. The sign chart just looks a little bit different. The first subinterval, I can plug in f of negative 10. So I'm plugging that in to the equation where it's equal to 0, or less than 0 in this case, which I did not highlight, I apologize. We're looking, again, our final answer is going to be where this graph is below 0, or red. So if I plug that in, negative 10 plus 9, so this guy right there, negative 10 plus 9 is negative 1, so that's a negative number. And then negative 10 minus 5, that's still a negative number. Negative divided by negative, that's going to be a positive, which means this graph should be above. I'm just going to write an A for above because I'm getting lazy. In the second subinterval, you could plug in the number 0. If we plugged in the number 0, 0 plus 9 is a positive number, 0 minus 5 is a negative number. Positive divided by negative, that's going to be a negative, which means that part of the graph is going to be below. In that third subinterval, we could plug in 6 or 10. 10 plus 9, that's a positive number. 10 minus 5, that is a positive number. Positive divided by positive, that is still a positive number, which means this graph's going to end up being, again, above the x-axis. But this particular inequality is asking me only for when the graph is below 0, or below the x-axis, which is the interval from negative 9 to 5. Now, why did I not include a bracket around the negative 9, specifically a blue one in my color scheme? Yeah, hopefully you're thinking, well, because you just want where it's less than 0, not equal to 0. So we actually don't want to include that bracket here. We just want a parentheses around negative 9 because we're not including negative 9 in the solution for where it's less than 0. Take a moment to look at B. Okay, pause the video and see. We kind of done the same thing here. Numerator equal to 0 to find the zeros of the function. Denominator equal to 0 to find what is called the vertical asymptotes of the graph, or the holes in the number line. And then we just need to make sure we know, once we've done our sign chart for the different areas or subintervals that we have, the first one, the second one, the third one, and the fourth one, we know what we're asking for. We're asking for the place where the graph is greater than or equal to 0. So the places that it's green or blue, and actually blue and not a hole, is from negative infinity to negative 4, and then from 4 to infinity. Why did I not include a blue 7 in my solution here, this guy? Isn't it already included in that domain from 4 to infinity? So you don't have to like point it out, like we get it. It's between 4 and infinity, the number 7 is there. And then last but not least, if you look at C, C is only different from the other two because why? Well, when we get started, we've been wanting this to be greater than or equal to 0 because we want to be able to compare it to that x-axis. And right now, we're comparing it to the number 2, and I don't want that. Okay, so let's again just pretend that this is set equal to instead of with an inequality, which means I can just move that 2 to the other side by subtracting. If I wanted to combine these terms together, they need to have a common denominator. So let's make the common denominator, instead of 1, let's make that denominator x plus 2 as well, which means I have to multiply by that scalar for the second fraction. Once the denominators match, we can just write it as one numerator and set it equal to 0 to find my zeros for this function. We distribute, and when we simplify, and thus we find that our 0 for this function is 9. We also need to know the asymptotes. Remember, the asymptotes is where the denominator is equal to 0. That is my domain restriction for this rational function. So x cannot be -2. So here's my number line from -infinity to infinity. I have a hole, or a vertical asymptote, at -2, empty. And then I have a 0 at 9. Okay, now at this point, we're trying to decide if this graph is less than or equal to 2. But when we resolve this, we're not only finding less than or equal to 2. When we rearrange this equation, when we got it to say 0, we're actually looking for where it's less than or equal to 0. That's going to give me the place that I'm looking, okay, to plug in my sign values, as well as know if I'm looking for where it's above or below the x-axis. So let's fill out our sign chart. There's going to be 3 subintervals here. You have your first subinterval, your second subinterval, and your third. My first subinterval, I can plug in -10. And when I plug in -10, this is going to be negative on top and negative on bottom, which means I'll have a positive or above. That second subinterval between -2 and 9, I could plug in 1, I could plug in 0, which is what I'm going to do. We'd get negative positive, which means it's going to be negative or below. And then that third subinterval, I could plug in 10, I could plug in 12 if I wanted, but I like to plug in 10. We're going to have positive, positive, which means this graph is going to be above there. But if you remember, what we're asking for is where the graph is below or equal to. So it's below in the second subinterval and equal to at 9. So from -2 to 9, including 9, is going to be the interval that solves this inequality. Complicated stuff, but if you keep things color-coded, I think this will be a little bit easier. Sign charts usually freak people out, but remember, you're just picking a number and plugging it in and deciding if the number that gets output is positive or negative. That's it for the sign chart.